There are several, well, many reactions actually that involve gases as reactants or products. When we have solids, liquids, aqueous solutions, mass or volume is a convenient way to measure them. Gases, we don't usually indicate their quantities in masses as grams, but the volume at a given temperature and pressure is how we would specify the quantity. So we're going to make use of the ideal gas law to find the number of moles of gas from a volume, or to find the volume from the number of moles of gas and its temperature and pressure. So this is a variation on our regular grams to moles to moles to grams. Here at the beginning, we could have pressure, volume, and temperature. We need all three of those to specify the quantity of gas. And then go to moles, and then we can go back to pressure, volume, and temperature of the product gas. But we've also learned a couple of other variations on this. We could have volume and molarity of a solution and go this way, and then end up with pressure, volume, and temperature of a gas. Or we could end up with a volume and molarity of a solution at the end. So there's lots of variations. The common theme in all stoichiometry problems is moles to moles in the middle. Whatever you're starting with, you have to get to moles. You convert that to moles of your product or the other thing you're trying to find, and then you convert that to the quantity that's requested. So let's do an example. In the following reaction, 4.58 liters of oxygen was formed at a pressure of 745 millimeters mercury and a temperature of 308 Kelvin. How many grams of silver 1 oxide decomposed? So the reaction that is given to us, I'm going to use the equation to organize the numbers. This is a stoichiometry problem involving gases. So 4.58 liters of oxygen. I'm going to write that under oxygen. 4.58 liters of oxygen. The pressure also applies to the oxygen. And the temperature is important. Those are the quantities we need to find the number of moles of oxygen. And the question is, how many grams of the Ag2O? So my path then is I'm starting over here. I've got pressure, volume, and temperature of oxygen. I need to go to moles of oxygen. Oops, wasn't looking ahead. And then I'm going to go to moles of Ag2O. And then I'm going to go to 2 grams. Any questions about the path? So how do I find moles of oxygen? Is that dimensional analysis? Not really, right? That's ideal gas law. So we're going to use the ideal gas law to calculate the moles of oxygen. So N equals PV over RT. That's just a rearrangement of the ideal gas law. Pressure is given in millimeters of mercury. Do you like the putting it over 760 in the whole equation, or would you rather I do it separately? In the equation? Okay. So I'm going to put the 745 over 760. And when I do that, I end up with units of atmospheres. And then I need the volume. The volume is given in liters this time, so 4.58 liters. And then down here I've got our old friend, R. And the temperature is given in Kelvin, so that's all very nice. And we calculate. And I'm getting 0.1776, 0.177. That's going to have 3 significant figures, and then I'll carry 2 extras. And the unit is moles of oxygen. That was our first step. Did everybody else get that number? If you're getting a really big number, you're having a confusion with your calculator, and talk to me afterwards and we'll get that straightened out. Now the rest of this is dimensional analysis. So 0.17763 moles of oxygen. I need to convert that to moles of silver oxide, and then to grams of silver oxide. So moles of O2 come down here, and moles of silver oxide come down here. Those cancel out. Where do we get the mole to mole ratio? From the balanced chemical equation. I want a 2 in front of the Ag2O, and here's an unwritten 1. I can leave it unwritten or I could write it down. And then we need the molar mass of Ag2O, 107.9. So we've got 2 times the mass of silver plus oxygen, 2 times 107.9 plus 16, 231.8. Skip the 2, 231.8. That's grams per mole. So that goes in here, 231.8. So now I've got my moles times 2 times 231.8. Now I can round this to 3 significant figures, and I'm coming up with 82.4 grams of silver 1 oxide. Any questions? Here's another one. How many liters of oxygen at STP are required to form 10.5 grams of water? This one could be done in 2 ways. STP tells us the temperature and the pressure. We're trying to find liters of oxygen. So the question is how many liters of oxygen, and we've got 10.5 grams of water. We could use the ideal gas law to calculate the moles of oxygen. And then from the moles of oxygen to calculate the liters. Or, as the title of this example suggests, we can use the molar volume. So molar volume at STP of any gas is what? 22.4. 22.4 liters per mole. So I'm going to use that one. So what we're starting with is grams of H2O. So we're going grams of H2O, always to moles in the middle. Moles of H2O. I don't know why it keeps doing that. Moles of oxygen, and then liters of oxygen. This is nice because this is all just one little conversion, and so I can just string this out and calculate liters without having to dig around in the ideal gas law. So 10.5 grams of water, 3 arrows, 3 conversion factors. Liters of oxygen on top. And then I'm going to put all my units in the bottom. Moles of water, to cancel moles of water, moles of oxygen down here. This is where the molar volume of the gas comes in, 22.4 liters for every 1 mole. That only works at STP, but this is at STP, 22.4 liters. The guy in the middle comes from the balanced chemical equation. There's an unwritten 1 in front of the oxygen, and there's a 2 in front of water. So I've got a 2 down here and a 1 up there. The molar mass of water, 2 times the mass of hydrogen plus the mass of oxygen, 18.016. So we've got 10.5 divided by 18.016 divided by 2 times 22.4. And looking at this, I should have 3 sig figs. So I'm going to round this to 6.53 grams of water. No. Liters of oxygen. It's too early. Any questions? I zoom in on my screen and then I can't always see what's around me, so I get lost a lot. What's next? Another example. Do you need another example? Or are you good? I think we're good. We're